Yo, hello. So I was literally just recording a different video. And I realised that I was wrong. I was wrong about something. I thought that our understanding of continental drift was developed in the 1960s, and I thought that it was crazy that we had, gone to the moon. Sorry, I don't think so. We've gone to the moon by now, by then. But we'd like sent a dog into space, and we knew about DNA by that time, and we known about all this different stuff, but we didn't know the land beneath our feet was moving. You know, I thought that was crazy. Turns out I was wrong, which makes sense that I was wrong. Turns out that we know, or we had known about roughly that the land beneath us was moving since the 1500s. And I looked it up on Wikipedia. I'm still not done with it. And I found some stuff, and I was seeing myself going into a rabbit hole, and I thought, what better to do than go into this rabbit hole on camera and just not on camera, record myself going into this rabbit hole of trying to figure out when we had these theories. Like I understand the theories, but I don't know when, or like when the time, what the timeline particularly is. So I wanted to do that. So if you'll give me a couple minutes of your day, hopefully we can both learn something together. So I think the first thing that I was looking at was plate tectonics. Actually, I was looking at Pangea before when we first thought of that. I want to look at tectonics first though. So, history of the theory. Oh, I love that it has this. Okay, cool. So, wow. Okay, there's a lot of stuff. Development of the theory was occurred in scientific date. Of a period of 50 years of scientific debate. The event, was para. Okay, well, was a paradigm shift, and therefore can be classified as a scientific revolution. Oh my days! I thought that was a geological term. Um, Now described as plate tectonics revolution. Cool. Around the start of the 20th century, so this is a date that I'd seen before, various theorists unsuccessfully attempted to explain the many geographical and geological and biological continuities between the continents. I knew about this. I think in geography in the UK, if you do it for GCSE, they tell you one of these continuities was that I think rocks were found in like two different places, and they were like the same. Couple fossil records that show this, so that'll probably be the biological. There's also like, I want to call it fucking the fact that like some continents just look like they fit into each other, like this bit of South America here. I don't know if you can see my mouse. The east coast of South America, and then the west southwest coast, I suppose, of Africa just look like they fit in nice and snug. It's very sunny out, which is normally very lovely, but it's making it very hard to see my screen. 50 years. Wegener. Okay, cool. I'd heard the name Wegener in my little pre rabbit hole. Expanded his theory in his 1915 book, The Origin of Continents and Oceans, starting the idea, also expressed by his forerunners, that present continents once formed from a single landmass, later called Pangaea. I think when did we start talking about Pangaea was a question I'd asked before. I'm going to quickly pull that up here. So, origin of the concept, Pangaea. Oh, wow. To first suggest, it's first suggesting though. I don't like anyone can first suggest something that can later come true. I don't know. Oh wow. Hold on. The concept that was later for. Okay, it's just the same guy. Damn, dude's a beast. So same dude. 3 years later. Sorry, wait, hold on. So 3 years prior to the origin of continents and oceans, he properly theorizes about Pangea. Didn't call it Pangea at the time. Wegener stated that these separated and drifted apart, likening to icebergs of low density sail floating on the sea of Densissima. Supporting the evidence, I came from the dovetailing outlines. Oh my days! Wait. Came from the dovetailing outlines of South America's east coast and Africa's west coast. Literally what I just talked about. Antonio, this guy, had drawn on his maps and from matching of rock formations along the edges, confirmation of their previous contiguous nature also came from fossil plants. Yeah, nice. This is what they teach you, I think, GCSE geography, maybe A level, I think. No, I think it was GCSE. All distributed across South. Nice. So all these like previously connected areas. The South African guy, geologist, put together such a mass. Okay, so this dude, this geologist, puts together all the information in 1937. Publication, Our Wandering Continents, and went further than Wegener in recognizing the strong links between the. Let's look into this. What's this? The Gondwana. Large landmass, sometimes referred to as supercontinent. The remnants of Gondwana in 2/3 of today's continents. So Gondwana formed of the large stable blocks of the Earth's crust. The collision of. Wait, I'm confused. I'm like mildly confused. So it's still supercontinent. It's just like a bit torn up, is what I'm getting from this. Began to separate from northern Pangaea. Oh, okay. It's a supercontinent, but it's like when Pangaea was starting to split up. I think. Somebody can correct me if I'm wrong. So unsuccessfully, I think. No, we'd already read this. Despite opposition during the 1920s, 30s, and 40s, the former reached important milestones proposing that Okay, wait. Despite much opposition, the view of continental drift gained support and a lively debate between the drifters and the mobilists. Prominent proponents of the theory. The fixists, who are the opponents. Wait, what? Oh, drifters or mobilists. Okay. So mobilists versus fixists or drifters. Okay. So this is when they had like mass debate. Seems like it was just between the 20s and 40s. The former, so the mobilists, I'll call them drifters actually. The drifters reached an important milestone, proposing that convection currents might have driven plate movements spreading below the sea of the ocean crust. Concepts close to the element plates. Geophysicists and geologists like these guys one of the first pieces of geophysical evidence that was used to support the movement of lithospheric plates from paleomagnetism. This is based on such fact that rocks of different ages show variable magnetic field. Oh, wait, hold on. Yes, I've learned about this before. Okay, I'm not going to read further. I'm going to close my eyes and try and remember. So the Earth's polarity of its magnetic field flips for some reason. I don't remember why. It flips like every 100,000 years or 500,000 years. And because the Earth is so old, because it's billions of years old, you can see like, or theoretically, I don't know if you actually can, on rocks like the pool of the magnets, and like it'll be like in one direction, and then like it'll switch, and then it'll switch, and then it'll switch, and that's like kind of like rings on on like inside of a tree. I don't. How does that work? How is it like the iron inside of the rock and it's like moving or something? I don't know. Um. So evidence by studies around the magnetic north and south pole reverse through time, especially important in paleotectonic theories. The relative position of the varies through time. Initially, during it also wanders a bit, doesn't it? Which in aviation and navigation can make it quite annoying, especially the closer you get to the poles. So like, how do I describe this? The closer you are to the poles, the more different your degrees are going to be. Yeah, because of like, it's the magnetic pole is different to your GPS pole, which is based on like 0, 0, 0, 0. You know, uh, pole wonder, see pole wonder, drifting alternative continents move in a shape. The second piece of evidence to support continental drift came in the late 1950s. This is probably what I was thinking of, and late 1960s. The bathymetry, what? Of the deep ocean floors and nature of. Oh my days! Why am I yawning? It's not that boring. I hope. And more generally, marine geology, which gave evidence to the association of along the mid-oceanic ridge. Publications. Wait, what? The and what? What? I'm confused. Simultaneous advances in early seismic imaging in and around these zones along trenches bounding continental margins together with many other geophysical and geological observations showed how oceanic crust could disappear into the mantle. Oh, okay, hold on. Okay. So subduction was one of the reasons we knew about drift. Mechanisms to balance the extension. All of this evidence made it clear around 1965 that continental drift was. Oh, okay, cool. So I was kind of right. It was made very clear and like I'm assuming somewhat accepted. The theory of appears in papers between 1965 and the theory, the implications of other studies. So I'm assuming it became consensus in the late 60s, but it's been theorized and worked on since the 1910s. Makes sense, I suppose. I guess. So I suppose I wasn't particularly correct. I wasn't particularly wrong, I suppose. And then this goes into even more detail regarding other things. But I think that summary does me pretty well. I do want to read about magnetic stripping, though, because I don't remember how it works. At the beginning of the 19th, using magnetic instruments, magnetometers adopted from airborne devices developed during World War II to detect submarines, began recognizing automatic variations on the ocean's floor. This finding through unexpected. Oh, sorry. You know what? Let me turn on my reading voice. This finding, though unexpected, was not entirely surprising because it was known that basalt, the iron-rich volcanic rock making up the sea floor, contained a strongly magnetic material, magnetite, and can locally distort compass readings. This distortion was recognized by Icelandic mariners as early as the late 18th century. Wow, 1700s, fucking hell. More importantly, because the presence of magnetite gives the basalt measurable magnetic properties, these new discovered magnetic variations proved another means to study the deep ocean floor. When newly formed rocks cool, such as magnetic materials, recorded Earth's magnetic field at the time. As more and more of the sea floor was mapped in the 1950s, the magnetic variations turned out to not be random or isolated occurrences, but instead revealed recognizable patterns. When these magnetic patterns were mapped over a wide region, the ocean floor showed a zebra-like pattern, one stripe with normal polarity and an adjoining stripe with the reverse polarity. The overall pattern defined by these alternating bands of normally and reverse polarized rock became known as magnetic striping. 1p equals striping, 2p equals stripping. I've been reading this wrong. And was published by Ron G. Mason and co-workers in 1961, who did not find, though, an explanation for these data in terms of sea floor spreading, like Vine, Matthews, and Morley a few years later. Okay, that's pretty cool. I didn't understand how we knew about magnetic striping. I suppose I do now. That is, yeah, pretty cool, I guess. I think this video is getting pretty long, and I think I'm done with this little rabbit hole that I've gone down. Yeah, I don't think I have anything left to talk about. I hope all of you enjoy your day. How long is this recording? 17 minutes, not that bad, is it? I hope you all have a very lovely day. I hope you eat well, sleep well, drink well, drink your water, eat your food, get your protein, get your carbs, get your fibre. Watch the roads, stay safe out there, and I'll see you lot later. Ta!